We begin this week with section 2.8. This is about the very important intermediate value theorem, or IVT. And what does this theorem say? Let's just recall it very briefly. The IVT says that if f is a continuous function on a closed interval of the form a b, then for every value m between f of a and f of b, there exists at least, and this is a very important part, at least one value c in the open interval, so it's not containing a and b, such that f of c is equal to m. And what does this mean? So we have a function f whose graph looks something like this. So we have the x and y axis, and it moves like that. So we have b and a, and here f of a is some number, and f of b is some smaller number. This is f of b. So if we pick any m in between these two values, if we go back to the domain of f, we'll find that there's one value c down here, such that that c is mapped to that value m. So the m will be in fact equal to f of c for that particular c that you can look at by going back, moving horizontally and then vertically down once you touch the graph of f. And this is guaranteed to happen when you have a continuous function. If the function is not continuous, then this is not necessarily true. And the moral here is that a continuous function cannot skip values. So if it attains the value 1 and the value 3, somewhere in between it must have attained the value 2, for example. So let's compare this with this continuous function. So this is a failure of discontinuous. To have C mapped to M. So let's look at a different graph. here we have some function like this, and this is A down here, and this is B, and so f of A is this number, f of A is this number, and f of B is this. Clearly this function here is discontinuous, so let's extend a little bit just to try to make sense of it. So there's a discontinuity at this point. And so what happens if we try to find a preimage for a value m? This value here is in between f of A and f of B. M is in between the two, this value and this one here. And if we try to go back and find a preimage for that, we'll continue forever because it's not possible. And that's because the graph of the function f has breaks. So the function is not continuous. So the hypothesis here that the function is continuous is essential. So it's a very important one. Okay, so the first thing to check whenever you're applying the IVT, and the first thing you need to state is that the function you have at hand is in fact continuous. Otherwise, you will not be able to apply the intermediate value theorem. So what's the first thing to check? Whether the function is continuous or not. Okay, so let's look at how to apply this. So let's look at some examples. First example using the book is to show that f of x is equal to x squared or x cubed plus 1. So f of x equals x squared over x cubed plus 1 takes the value 0.4. So let's stop right here for a second, and let's notice here that the statement of the intermediate value theorem contains some piece of information. One is that you have a continuous function f. We have that in this example, and it's defined in a closed interval. Okay, and then inside that interval, f will attain any value in between the values f of a and f of b. So if we want to apply this, we need to restrict the domain of f to a closed interval. But the closed interval is something that will be convenient for that particular problem at hand. So usually the numbers that we will use are very simple. So either 0, 1, or they will be given to you. So consider the function f defined on a given interval. So from 3 to 7, say, and then a and b are given to you. But if not, the endpoints that you must look for are rather simple. So 0, 1, or something really negative, or something really positive, and those are the combinations. But try to look for the easiest things, the easiest numbers to deal with. Perhaps some fractions like 1/2 may show up, but that's less frequent. So in this particular case, since we want to, we're aiming for 0.4. So the idea here is to find a value a and b with b greater than a, such that 0.4 is between f of a and f of b. So what are good candidates for a and b? Well, you know, if you look at this expression, you'll realize that when x is equal to 0, this expression takes on the value 0. This expression over here, since the numerator becomes 0. Okay, so, and then what about 1? When x is equal to 1, the numerator is 1, and the denominator is 2, which is 1/2, or 0.5, which is slightly greater than 0.4. So we have found 2 points. We found 2 points such as the values of the function. These 2 points are respectively smaller and greater than 0.4. So let's try a equals 0 and b equals 1. So this is the sequence of steps that you need to follow every time you apply the intermediate value theorem. So step 1, f is continuous. Okay, x is f of x continues on a b, on the interval ab, which in this case is the closed intervals 0, 1. Well, is it? X squared is a polynomial. X cubed plus 1 is a polynomial as well. So these two functions are continuous. Now, the only problem could arise if x cubed plus 1 vanished in between. Sorry about that. If x cubed plus 1 were to vanish between 0 and 1. But that's not the case. It's not the case. So x squared is continuous everywhere, and so is x plus 1. Now the second thing is x cubed plus 1 is positive throughout the whole interval for every x in 0, 1. So we can apply the rule of the quotient, and we have that f of x is x squared over x cubed plus 1. This is continuous and not 0, in between 0 and 1. So this whole thing then is continuous. Remember, the quotient of continuous functions is continuous if the denominator doesn't vanish, it doesn't produce any problem, which is the case. Okay, so this shows that f is in fact continuous. So the first step. I mean, I'm just going and showing every detail. This first example. Then we will just brush it off. I mean, it's but most of the functions we'll give you will be continuous. So it's just a matter of checking. So you're saying polynomial divided polynomials, the denominator doesn't vanish. That's it. Okay, step 1 is always checking that the function is continuous. What is the second step? Then, so step 2 will be to guarantee that 0.4 is in between f of a and f of b. So 0.4 is in between f of a and f of b. Is this the case? Well, yes. So f of 0, remember that a is equal to 0 in this case, is equal to 0 squared over 0 cubed plus 1, which is just 0. And this is less than 0.4. Now, what about f of b, or f of 1? because that's what b is equal to, will be 1 squared over 1 cubed plus 1, which is 1, and 1 is greater than 0.4. So in sum, f of 0, remember that this is equal to 0, is smaller than 0.4, which is smaller than f of 1, which is equal to, oh no, this is equal to 1/2, I'm sorry. Equal to 1/2. 1/2, by the way, I mean, in case you're not convinced, is equal to 0.5. So 0.5 is certainly greater than 0.4. Okay, so now that we have this, the value 0.4, the value we're aiming for, is in between the values of the function at the endpoints. Then we can apply the IVT. To conclude that there must be a C, and in fact the C must be a number in between 0 and 1, such that f of C is equal to 0.4. Okay, so it's always like this. So we first prove that f is continuous. Then after that, we show that the point, I mean the value we're aiming for is in between the value of f of a and f of b. And finally, we can conclude that there is a point in between the endpoints, such that f at that point is equal to the given value, in this case 0.4.